This is Software Engineering Radio, the podcast for professional developers, on the web at se-radio.net. SE Radio brings you relevant and detailed discussions of software engineering topics at least once a month. SE Radio is brought to you by IEEE Software Magazine, online at computer.org/software.
This is Robert Blumen for Software Engineering Radio. I am joined by Michael Hunger at Graph Connect 2012 in San Francisco. Michael works for Neo Technology on the Neo4j Graph database. Michael is also the project lead for the Spring Data Neo4j project. Michael and I will be talking about graph databases. Michael, welcome to Software Engineering Radio.
Thanks, Robert. Thanks for having me.
Michael, please tell the listeners a little bit about your background.
Yeah, I've been active in software development ever since I was a kid, so I started programming at an early age. And ever since, I've been really interested in programming languages, computational problems, working with the people that develop software. I've been writing a lot, I've been speaking at conferences, and I try to share the knowledge I learn in my life with other people. And so the first contact with Neo4j and Neo Technology was like 4 years ago. And back then I was really interested in what graph databases are good for. And I really got addicted with graphs and graph databases like Neo4j. And so I stayed and have had a really great time ever since. And besides the Spring integration, I also work in the Neo4j community team. So working with our big open source community of developers, and it's really a great place to be.
Michael, we'll be talking about graph databases. Let's start out by talking about graphs. What is a graph?
So I want to start by not defining a graph mathematically, but by asking you to look around you. So the world we live in is all about connected things. So we are connected to other people, we are connected to events, we are connected to things, to places, to actions. So it's all about relationships, it's all about connections. Our whole life, our whole world is about that. And graphs actually represent this information. A graph consists of nodes and relationships between those nodes, and both nodes and relationships can hold properties. At least this is the structure of a property graph. And this data structure is very versatile, so it can store arbitrarily structured data and allows you to easily model complex domains with lots of connections, and allows you to actually navigate those relationships to gather the information from the graph that you're interested in. If you look at it from a historical perspective, graph theory was actually dealt with by Leonhard Euler about 300 years ago in Königsberg, when he looked at routing and pathfinding problems. And ever since, mathematicians have been really thrilled about graph theory. But graphs in your everyday application development are not that old. So there were network databases in the 70s, but actually graph databases only appeared around 2000. And that's where we are now, in a boom year of graph databases.
So say a little bit more about what is a graph database.
A graph database is a native storage engine that is able to store and retrieve graph structured data, meaning nodes and relationships and properties on nodes and relationships, in a fast and cohesive manner. So graph databases are mostly fully transactional, so they fully support the asset operations of transactions, and graph databases are very well suited to quickly navigate large networks of elements, meaning graphs. And in general, graph databases are often different from other databases that we know because they have a very distinct data model and very distinct applications. So we can use graphs to model any kind of domain model or object model, but we can also use graphs to execute some very interesting operations like path finding, routing, recommendation systems. PageRank is another example for that. And so graph databases support both. So the usual mapping of complex domain models and also these specialized use cases that graph theory is all about.
Does an application that's built on a graph database have a data model beyond having nodes and edges?
Yeah, so every application has a data model. I don't think there's an application without a data model. And the data model is in any case in the application. And with each NoSQL database, the data model will mainly reside in the application because most NoSQL databases are schema-free. That doesn't mean they don't have structure, but the structure does not live in the database as an explicit concept, but it lives explicitly in the application. And the database doesn't constrain you up front with the structures that you want or think you want to have in the database, but allows you to grow and evolve your data structure as you evolve your application. So the data model is there, it's in the application, and in the graph database itself, you can retrieve or imply the data model from the types of nodes and relationships that are available in your graph, but it's not a closed thing, but it's a kind of an open model that can be evolved at any time without changing or modifying a schema definition or something like that.
Michael, you said a graph database is good at modeling many different kinds of problem domains. I can easily see how a problem like social graph in a social network, which has the word graph as the name of part of the domain, could be modeled as a graph. But do you see graph databases as having a broader application and possibly being a superior model for many different types of problems that we might not be accustomed to thinking of as graphs if we're used to relational databases?
Yeah, if you look at the relational databases, so many people confuse relational databases and relationships, but relational databases are about relational algebra, which is a set-based algebra. So where elements of very similar structure, large amounts of elements of very similar structures are handled by operations like filtering and aggregation and projection and so on. Graphs, on the other hand, are about a very fine-grained data model that's about nodes and relationships. And in general, graph databases can model complex domains very easily. And it's, as they are mostly about the association, so every domain that has a large number of associations or relationships benefits from the graph model. Also, the typical object model benefits from the graph model as well, because we don't have the well-known object relational impedance mismatch there. And we can, if you look at our application and at use cases of the application, and we see that the application deals with connected data structures or with connected data, then a graph database is usually a good fit for this kind of application. You should also look at the data structure itself. So is the data itself connected? And also at the data volume. So if I have a lot of very, very simply structured data, like billions and trillions of elements, then probably a key value store would be a bit of better fit. If I have very similar structured data in usual volumes, then like for instance salary lists or product lists or something like that, then a relational database is a better fit. But as soon as I look at connected data, then a graph database is usually a good fit for this kind of application and data structure.
What you're saying is choosing the right data store, then it depends on the whether your data model is very connection heavy and what type of access patterns. If the access patterns involve traversing a lot of relationships, then a graph database might be the best choice for that.
Yes, that's correct. So like in any other case of polyglot persistence or NoSQL, making informed decisions about which data stores to use derive from the data structure that you have and also from the use cases in your application. That's what it is all about. So NoSQL is not about SQL or not SQL. It's about having a choice of databases and choosing the right databases for your application by looking at your use cases and your data structure. And if your data structure and use case point to graph databases, then you would include a graph database in the set of databases to use. If they don't have such properties, then you wouldn't want to look into graph databases.
Are you seeing a lot of application architects partitioning their data into different subdomains based on characteristics of the data and access patterns and using a graph database for one of those partitions and relational for another one and so forth?
Yes, actually, we see both. So we see people partitioning their data according to access patterns and use cases, and then using different NoSQL databases, for instance, a graph database and a column database, or a graph database and a relational database. So some people also move out all the connection-heavy data out of their relational databases, keep all the connection in the graph database like Neo4j, and just keep the tabular information in the relational database. But we also see people that completely move to a graph database for the whole application. And I think one of the reasons for that is with a graph database you get the durability and atomicity and isolation properties of transactions. And so people trust graph databases as their kind of single source of truth because they are used to these guarantees from relational databases. And so they have easier time trusting a graph database to be the kind of the master store of their data. So actually we see lots of different application architectures, and both are valid architectures. So there's no kind of one best way of doing that. It's always very dependent on what you need and what you want to do and what your experience is and so on. So there are lots of factors that influence which way to go.
One of the things I have been gradually understanding about the NoSQL world is that consistency is more of a dial that can be turned based on a degree of availability and distribution in the data store. Is it inherently the case that a graph database must supply the ACID model, or can those things really be considered separately? Could you build a graph database that was more base rather than ACID?
So in general, choosing or looking at the cap theorem and at base is mostly required for people that have a really large amount of data that they can't handle in a single instance. So they have to short or scale out. Actually, what we learned is that most of the typical business use cases don't have these large amounts of data. A graph database can still support billions of nodes and relationships in a single instance. So that's mostly not a problem. You can easily scale out for reads by replication. And if you look into sharding or scaling out, then the consistency dial, as you said, is only if you look across the cluster. So on a single machine, if you write something to a single machine, it will still be there. But if you look at the whole cluster, it takes some time to propagate, for instance, to other nodes of the cluster or other machines of the cluster. And that's the same with graph databases. As soon as you put a network in between database instance or database machines, then you have latency about distribution of information. And having global transactions across a cluster is, of course, much more expensive than having local transactions on a single machine. So also in Neo4j, in our cluster mode, we have eventual consistent setups where you can say, okay, I don't need fully asset capabilities across the cluster. It's okay if I have just a write Chrome of two machines or something like that. Then I write to one machine, this machine connects to another one, and they grab a log, and then the information is synchronized on those two machines, and the other machines of the cluster will get the information propagated. So it all depends on your needs. So if you want to have your data always consistent and always available, then you would still go with an asset model. But if it's okay for you that you have a stale reads, for instance, then you can also, of course, choose with a graph database to go this route. That's about the replication. The sharding is a different aspect. When you get a graph that's so large that you can't run it on a single instance, and you have to shard it, then you get into a very interesting problem, because sharding graphs is an NP hard problem, especially if you have graphs that are stored in graph databases, because those graphs are not static but dynamic. So every time you change the graph, its structure is potentially also changed. And when you chart a graph, you usually tend to take isolated subgraphs, so parts of the graph that have just a few connections to the other parts of the graph, and put them on different machines or different charts. And as soon as you work on the database and insert new elements and new relationships, you of course also change the structure of the graph. So your sharding algorithm or your sharding distribution that you chose at one time might not be true at the next moment, because the graph structure changed. So a general sharding of graphs is a very hard problem. So we're working on that, of course. But in general, you usually shard on application level. So for instance, when Adobe installed their Neo4j cluster globally, they sharded by geography. So they had a cluster for the US, one for Europe, and one for Asia, and they were synchronized across the globe. But of course, each of them was independent and had a looser consistency approach there.
Michael, you said a moment ago that quite often all of the significant data for an application can fit on a single node. Can you give us some approximate numbers for Neo4j of how many nodes and edges can be stored on a single average size server?
Yeah, so a single Neo4j instance can store 34 billion nodes and 34 billion relationships, and which will increase to by a factor of 4 or 8 in the next year. And this is already beyond the needs that so far all our customers have. And the interesting thing is also about as you said, the choice of the NoSQL database that you have for a certain use case or a certain data structure implies the database. So you wouldn't use a graph database, for instance, for storing very low-level, large-volume data. So you wouldn't take a high-volume event stream and store that just in the graph database, because the graph database is not something you would store such kind of data in. You would choose a key value store or column store to store this data in. What you would store in the graph database, on the other hand, would be the higher level abstractions that you could retrieve or extract from this event stream. So the model that you would derive from the low-level data, that would go into the graph database. And that's also what our users and customers do, be it in finance or genetics or other sciences. They look at these, or telcos, they look at these low-level data streams, extract the relevant and interesting information, and put that into the graph. And so the data volume that the graph handles is much smaller in volume than the original data stream, but it's much richer in information and also much richer in connections, because that's where the actual value lies in this data. And then people can look at these graph models and make decisions, run algorithms on top of that, or work with this data in general.
Is graph database more suited for applications that are more read intensive than write intensive?
That's a good question, actually. Graph databases in general are more supportive in read loads than in write loads, because due to the transactional constraints, each transaction commit has to be flushed to disk. And so if you have a high sustained write load, and then your write throughput is limited by the speed of your disk system. But then the data is also durable. So if you have a power off in the middle of a transaction, then you don't lose any data. That's the benefit on the other end. It's optimized for reads, because graph databases also move the cost of creating relationships to the insertion time. So at insertion time, when we say you and me, for instance, are connected, this relationship is actually stored in the graph database as a record. But that makes reading or following connections or relationships very fast, because there's just a record that I can take and follow. And I don't have to recreate the connection by pulling tables or lists of elements into memory and finding matches, and then from those matches derive the connection at query time. So that's why the query part is much faster in the graph database. And we've also seen that graph databases can, for instance, execute join-heavy queries up to 1,000 times faster than a relational database. And so you're right in your assumption that graph databases are more suitable for read loads than write loads.
I would characterize a relational database in terms of query performance as the number of rows it can consider and the number of tables involved. How do you measure or quantify the read performance of a graph database?
In general, as graph databases are about local queries, so you take one or more starting points, for instance, users or products or movies or songs or something like that, or places. And from those starting points, you navigate a graph. So the navigation, so the traversal or the hop from one element from one node to another is a constant time operation, because we have the pre-computed and pre-stored relationship records. So your query is actually only depending on the number of elements you touched during the traversal. So from the traversal depth and breadth depends your query performance. What doesn't impact your query performance is the total size of the graph, or the total amount of data, because you always have local queries. So you're not interested how many other people are living in the world if you just want to retrieve some information from your friendship graph, for instance. And you're also not interested in how many products are in a certain data warehouse if you just want to compute a recommendation for a certain category or something like that. Query performance in a graph database is determined by the number of steps you take in your navigation of the graph. That's the only thing that determines the query performance. And both data volume and join complexity does not impact the query performance in a negative way.
Michael, I think it might help us all to understand this graph model if you could give us an example, or maybe a toy example, of a problem from a business domain and how it would get mapped into a graph abstraction.
Yes, so there are lots of business domains we could choose from, and let's take a movie database as an example. So I have in the movie database, I have movies, I have actors, I have directors, I have users, I have roles that actors played in a movie, I have ratings, I have reviews, comments, and so on. So all of these are elements, and all of those elements are connected. So let's look at the main elements, which are the movie, which will become a node with properties like title and publication year and so on. Then we have the actors, which are also nodes with their names and birth dates and so on. The relationship between the movie and the actor is actually interesting because this role, which would end up in a relational database as a join table, most probably, will just become a relationship between the two. And all the information about the role, like the money he got and the role name and the whatever other information is on that, would live on this relationship. And this relationship could be, for instance, an acts-in relationship between the actor in the movie. So I could say this actor acts in this movie, and that defines the relationship type, which is acts in the direction from actor to movie. If I look at the other elements, for instance, a user can be, for instance, friend with other users. So if a user have friends relationships to other users. And then a user could, for instance, rate an actor in a movie. So there will be also a rated relationship going from the user to the movie and from the user to the actor. And the rated relationship could, for instance, contain also information like how many stars you give the movie or a comment on the movie or something like that. And with all these things in place, we then can say, okay, we can easily build a movie database application on top of that because I just have all my elements in place, all my objects, all my types. I can use an object graph mapper like Spring Data Neo4j for retrieving the data from the database and storing it back. So just basic CRUD operations. And where it gets interesting is when I want to, for instance, compute recommendations for users. So I want to see which movies could I recommend to this user to watch. Right. So I could, for instance, look at the friendship graph of this user and see which movies his friends like, and recommend the top 10 movies there. But I could also look at the movies a user rated positively, look at other people which also rated these movies positively, so which are kind of similar to this initial user, and then look at those movies that those users also liked and that our initial user has not seen yet. So that's a typical recommendation algorithm, which is also called collaborative filtering. And so I try to find similar people, and then I look what those similar people also did or liked. And that's kind of a two-line expression in a graph, and would be a very complicated join in a relational database and very expensive join. And it's really, really fast to do something like this with graph database. That's a simple example of how you can employ a graph database to model your application and your domain.
The query examples that you're giving, Michael, I find them quite interesting because those queries would be difficult to do in SQL, would probably involve writing some kind of logic that mixed in a declarative programming language with a series of SQL statements and unpacking the results, whereas you can do that natively in a graph database very efficiently. Once you get your mind around these type of queries, does that change your design and thought process of how you think about the application?
Yes, it usually does. It moves your thinking more around the use cases. So you go away from just thinking about data structures to what you actually want to achieve. And then this also allows you to, for instance, add additional relationships to your domain model that support your use cases. So, for instance, if I get another use case in that says, I don't just want to recommend movies to people, but I also want to recommend people to movie studios or labels, because I have, for instance, in my database a really good set of people that are really interested in movies, and that could be a good set of reviewers for movies, right? So I would turn the whole thing around and say, okay, I have this existing model, and it's really very easy to just turn the query around and say, I'm not looking at the movie anymore, but I'm looking at the people in my graph, and I can, for instance, create recommendation sets for movie labels from people that would be really valuable for them, either by for advertisement or for being reviewers for their movies. So that having the data in the graph allows me to add another level of use cases very easily, and it also allows me to add other domains very easily. So for instance, if I add to this movie database location, so I know the location, for instance, of my users, then I can do all the local event, cinema, going to movies with friends thing very easily just by adding this geo information. Or if I add another part of the domain like TV series or something like that, then I can easily add to the recommendations that I make for people what to do tonight, and not just going to movies, but also just watching something that I have wanted to watch but I didn't know on TV, right? So it's adding more domains to a graph makes it actually richer and allows it to answer more interesting questions with more valuable answers, actually.
When you start thinking about problems in this way, does that change how you think?
That's an excellent question. Actually, a good question is if how you think affects how your data model looks like, or how your data model affects your thinking. Because if you look at whenever we are working creatively, so when we discuss things with people, when we go to a whiteboard, when we brainstorm, when we doodle, when we design things and so on, we often tend to draw graphs on our whiteboards or on our sheets. Even mind maps are graphs. And so that got me thinking if kind of the graph-like thinking is more part of the creative process, and if the kind of the tabular and list-based structure of relational database is more kind of the data management logical part of our left hemisphere, kind of. So the kind of analytical part is more the tables and lists, and the creative part is more the graphs and visualizations and complex and interesting networks thing. So that got me thinking if somehow this is all related. And of course, our brain is also a big network. So we have a graph in our head as well.
We've been talking about Neo4j. What are some of the more popular graph databases out there in the market, including open source?
Yeah. So actually, Neo4j is an open source graph database, and has been around for a while. So it started development of Neo4j in 2000 as part of a content management system, actually, and was then pulled out later. And so there are quite a number of graph databases around, and we see new graph databases popping up every other week. So 2012 has been the year where we have seen a huge increase in the number of graph databases. So other graph databases are OrientDB, there's DEX, there's Infinite Graph from Objectivity. There is also HyperGraphDB, there's Titan. There's from Microsoft, there's Trinity, FlogDB from Twitter. There are graph databases, internal graph databases at Google and at other companies. There is Cray with their hardware-based graph compute engines. There are other graph processing frameworks based, for instance, on Hadoop. And there's really a large ecosystem of graph databases out there that people can look at and choose.
What do you think is responsible for this rapid growth of interest in graph databases at this time?
That's also a very interesting question. So I think one of the main drivers for the interest in graph databases is that right now we are trying to derive more value from the connections between people and things. So first of all, we started exploring the personal social networks of people that easily extends to other places. It extends to their workplaces. So we see new types of job applications coming out. It extends to their buying behavior. What do I like? Things like Pinterest and so. It also extends to the places we are. Like if you look at Foursquare, for instance, that's also very location-based services. It's all about having people and things being connected to each other. It's also about the more and more available information devices all around us, the Internet of Things and so on. So it's the kind of the focus on moves from the individual items, which kind of are looked at just atomically, to the network of, or the rich network of interconnected elements. And to handle these kinds of data, you need a database that is able to store and work with this data efficiently. And so the interest in graph databases is obviously driven by this need to focus on the relationships much more than just the individual elements. And also if you look at something like the Google Knowledge Graph, so there's so much information and knowledge hidden in the connections between things, which can also improve the quality, for instance, of search results or the quality of algorithmic results by orders of magnitude. So Google employed lots of people and lots of hardware and lots of algorithms and to improve the search results by developing the Google Knowledge Graph, for instance, which kind of takes search to the next level. And that's kind of a trend that started, I don't know, 4 years ago, and will kind of increase exponentially over the next few years. So there will be more graph databases, bigger graph databases, and I think everyone will have a graph database.
What are some of the differentiating factors between the different graph databases?
In general, there are factors that differentiate graph databases on the data model. So Neo4j and most of the other popular graph databases employ the property graph, which is nodes and relationships with properties on both. Then there are the RDF triple store graph databases like Allegro Graph and lots of scientific projects which store triplets of data like subject, predicate, object instances, and they are very well used in the whole semantic web linked data initiatives and also at universities and so on. And there's another graph model that is called the hypergraph model, where a relationship doesn't just connect two nodes but an arbitrary number of nodes, which is suitable for a certain kind of problems. So what we've seen so far is that people tend to get their head around the property graph model most easily because it's very similar to the object model that people work with. And other differentiators between graph databases is if they're able to distribute or not. Some graph databases add additional capabilities, like ONDB also provides an a document view on the graph. Other graph databases have certain characteristics in data volume, query time. It depends on what the different vendors wanted to focus on. Something like Neo4j is more a general purpose, versatile graph database that you can do everything with, but you might, for certain problems at the kind of edges of this problem domain, might choose different products for that. And so then another differentiator is of course being open source or closed source. So things like Neo4j, ONDB, and Titan, for instance, are open source graph databases, and others like Infinite Graph or Allegro Graph are commercial proprietary graph databases which are not open source. And then there's of course also differentiators in terms, for instance, of community engagement and so on, but that's not technical.
Is there anything like a standardized query language that most graph databases support, or does each one take its own approach to queries?
Yeah, so the area of graph databases is still pretty young. It took a while for the SQL standard to evolve, and so the graph database at some point will also evolve a standard. Right now, everyone has its own solution. So there's, for Neo4j, we have a graph query language is called Cypher. ORDB, for instance, supports a SQL-like query language. Other databases support things like Datalog or Prolog as query languages. There's a framework, an open source framework that is kind of provides the minimum API of a property graph database, which is called Blueprints. And there's a query language, an imperative query language sitting on top of that, which is called Gremlin. And many of the property graph databases support this. It's actually a DSL sitting on top of an API. It's not a kind of textual query language per se. So it's a Groovy-based DSL for a kind of minimum common API across graph databases. But beyond that, there's so.
Michael, how do you evaluate the ecosystem as far as mapping tools between the programming language and the database? Or maybe I should start out saying, is there a need for a mapping layer to help the programmer persist their objects into the database?
First, let me answer this question in two parts. First, there's the problem on how to talk from a programming language with your graph database in general. That, of course, depends on the API that the graph database offers and on the community. So we were quite fortunate in Neo4j as open source community. We have a lot of people providing drivers for all the programming languages, or most of the programming languages that are out there for Neo4j, both for the JVM embedded version of Neo4j as well as the server version. And other databases have similar approaches, so that you have kind of the low-level access is the a driver for your language. That's the kind of the first requirement that you have to fulfill to talk to the graph database. And secondly, the mapping tools. It's a really interesting question. It seems that people want to have those, so it is kind of a boilerplate effort to write the mapping on your own. And so, like with relational databases, people wrote object relational mappers. People also write object graph mappers. Spring Data Neo4j is, for instance, one example of an object graph mapping tool. There are a number of others as well. Yeah, it depends. So it's kind of more of a convenience. So you could, of course, write this on your own in a limited amount of time to kind of cover the needs that you have. But there are actually some tools around it. And so people seem to like it and seem to use it, but they should be also always aware that putting an indirection layer between a graph database and your actual algorithms doesn't help with high performance things like massive data ingestion or extraction or graph algorithms. You should really run those things within the database, not pull the data out and run it outside. But it's really convenient, for instance, for integration with other libraries, for UI frameworks, and for basic CRUD operations. It's quite nice to have an object graph mapper around.
Are there any other aspects of the graph database ecosystem you're aware of that people should look into if they're using a graph database?
Yeah, one really interesting aspect of graph databases is that are really visualization heavy. So a graph in general has the nice property of being mappable from for instance, from a whiteboard drawing directly into the database. So if you stand by a whiteboard with some colleagues or a domain expert and discuss your domain and the elements and the relationships that are in your domain, and draw something that everyone agrees on, you can put the data in the graph, and when you visualize it, it's actually the exact same representation as you had on a whiteboard. So there's no kind of mismatch or transfer loss of information between a drawing, which is also a graph, and the database. A fun fact of that is that even relational databases model their data structures as graphs. So each entity relationship diagram that you've ever seen is actually also a graph that you model the relational database with. But in general, the visualizing what is in your graph database is a very important thing to interact with your users. So people tend to have a lot of visualization interest in visualization options. And there are lots of frameworks out there for visualizing graphs. There's Gephi, which is a Java-based framework. There is a lot of JavaScript-based frameworks for visualizing graphs, like D3, for instance, or Sigma.js. And this is a very, very important aspect. So people always ask for, how do I visualize my data? How can I see what's in the graph? How do I can I reason about it? And how can I find patterns in the graph by just looking at it? And that's kind of also what I spoke about before, this kind of higher level information that you extract out of low level information, put that into the graph, and then you can visualize it. And then you can easily see something like clusters or outliers or dense connections or important hubs in your graph and so on. So there's a really easy way of kind of getting a first glimpse of the data that you have in the graph with visualization. So the ecosystem of visualization tools is very, very large in graph databases. Another important aspect, of course, and the differentiator is graph algorithms. So there are lots of different graph algorithms, be it for path finding, for routing, for collaborative filtering, recommendation systems, things like PageRank, or algorithms for predicting for instance, language analytics. We had a project from some young students in Germany, which ingested the Google Ngram data of word probabilities into a graph database, actually into Neo4j, and we were able to predict the next word following the current one with a very high probability. So something like that is also possible. So the whole area of graph algorithms is also something that kind of differentiates graph databases from other databases and gives you really a high leverage, because with a good algorithm you can kind of beat your competition easily for deriving a certain information out of your data or a certain value from your data. And there's also kind of different support of graph algorithms across the databases. And but you can also easily just read about them, implement them on your own. And that's really easy to do with most graph database APIs. So that, it's not kind of like rocket science to implement the graph algorithms in a graph database.
Does the user of graph database need to understand the graph algorithm that the server will be using to do a particular query or operation?
It depends on the user, of course. Usually they don't have to understand it, because they can easily formulate what they want to have or what they want to see by just specifying a pattern in the graph. So imagine you have a graph of users having rated movies, as we talked about before. Then you can easily specify a pattern that you would say, okay, starting from this user, I want to see, or I want to go to all the movies that he rated, and from those movies I want to go to all the other users that also rated these movies, and from those I want to go to the actors that they liked or something like that. You just kind of specify the pattern or the path that you're interested in, and that's kind of nowhere near a graph algorithm, but it's already very, very powerful in allowing you to derive the interesting information out of the graph. Only if you have really specialized problems, like for instance routing or so, then you should be aware about that there are graph algorithms for routing. But what you actually do is just you supply the start and the end node of your routing problem, like the two cities you want to connect, and then you just tell the database to go ahead and provide you the top 5 shortest ways between those two cities, and that's about it. So most of the graph algorithms themselves, you don't have to understand them. You just need to know what is their kind of API, what do they expect as input values, and then they provide you with paths through the graph or other information that you can use to solve your actual business problem.
Tell us a little bit about Neo4j, the product that you work on.
Neo4j is yeah. So Neo4j is actually one of the oldest graph databases and also one of the biggest. So it has a really large active community, a large customer base as well. We've grown from 10 people when I started to more than 50 now within a few years. And Neo4j is a native graph database, so we have our own native storage engine, so it's not sitting on top of some other product. And it's written in Java, so it utilizes JVM, so it's also portable across platforms and can be embedded in other Java applications, which is really a nice feature for both high-performance applications and also for testing as well. You can get started with Neo4j very easily. We have a website, neo4j.org, that gives you lots of information and lots of screencasts and videos. We have also a manual that is actually quite interesting because it's not just a manual, but it's also generated from tests. So it's not just written text, but it's when running tests, we generate code snippets, results, representations, graphs, and so on from parsing unit tests that will end up being chapters and sections of the manual. So we are always up to date in the kind of information we have in the manual, which is really convenient and very, very nice. And there's also a very large user community around Neo4j, so lots of people on the Google group, on Stack Overflow, and so on. And as I said, we have the big advantage that there are many Neo4j users who felt the need for a driver for Neo4j in their own specific programming language, and if there wasn't one, they just started to write one. And most of those were actually using Neo4j in production or customer projects, so their drivers are also of really high quality. So that's a really big advantage of being an open source database, so that we didn't have to invest lots of people and lots of effort to develop and support all these drivers on our own, but people that are really experts in those languages were able to write those drivers for Neo4j. So being an open source database with a very active community is a really great place to be in and to work with. And so I would encourage everyone to just grab a copy of Neo4j, take one domain model that you're interested in and play around with it, try to visualize it with the integrated visualizer, run some queries on top of that, and imagine how it could look like in your next project or application to use a graph database. And I also want to encourage everyone to kind of open your eyes and look at the world by looking at the connection between things and not so much at the things themselves, and to see how much of our everyday life is a graph and is connected. Of course, it gets really addictive if you start doing that.
And tell us about your open source project, the Spring Data Neo4j.
Yeah, Spring Data Neo4j is the founding project of the Spring Data project, which is an initiative by SpringSource to provide a convenient access layer to the many NoSQL databases that are out there. So we know that SpringSource has done a good job at providing a convenient access layer to relational databases with the JDBC abstractions and also the JPA abstractions. And so in VMware, SpringSource, the Spring Data project is a quite important strategic project. And it was actually started by Rod Johnson and my CEO, Emil, sitting together, discussing NoSQL, discussing the relevance of NoSQL for Spring, and starting to work and actually code on the first iteration on the Spring Data Neo4j project, which is quite interesting. So it started the whole movement, and Spring Data Neo4j itself is an object graph mapper. So it takes your domain objects that you annotate, similar to GPL objects. You just annotate your objects, and then Spring Data Neo4j offers you a very convenient and straightforward mapping from those objects into the graph. So you can easily create your domain model as Java classes, where properties of the class or fields of the classes are mapped into either properties of the nodes, or actually references to other objects are mapped into relationships to other nodes in the graph database. And as relationships are also first-class citizens in the graph database, so they are in Spring Data Neo4j. And so you have a really easy way to integrate the graph database with existing libraries, with UI frameworks, and with other places in the Spring ecosystem as well. But you have at all time the ability to drop down to a lower level API, which gives you the high performance graph operations, which are not impacted by the intermediate layer. And Spring Data Neo4j also offers a really nice repository approach that all the Spring Data projects support, which allows you to write data access layer without actually writing code, by just defining interfaces with methods. And on those methods you can either have the infrastructure automatically derive the queries that they stand for, like in Grails or Rails, or you annotate the methods with the queries you want to execute. So it's very thin and convenient layer for abstracting the access of the underlying database via such a repository approach. And it's open source, Apache licensed project, part of the Spring framework, Spring Data project. And I'm really happy working with VMware and the Spring source engineers on that. It has gotten quite a lot of traction, and even some of our bigger customers are actively using Spring Data Neo4j to develop their business applications on top of Neo4j.
Michael, tell us about how the Neo4j open source project is structured and what role is served by Neo Technologies. What role does the community play?
Neo4j in itself is an open source project. It is available on GitHub, so all the source code and development is publicly visible, as well as our issue tracking and so on. Neo Technology supports the project by employing the engineers that work on Neo4j, but we always welcome contributions from the community. We actually are really interested in our community because they provide us a really great feedback and support for Neo4j. So we're getting a lot of really first-class feedback back from our community. And Neo4j is also licensed with an open source license. So Neo4j Community Edition is licensed with GPL version 3. So it's similar to MySQL. And Neo4j Enterprise license is licensed under HGPL. So when you're open source, we are also open source. And when you're commercial, then you can acquire a commercial license for Enterprise. But you can also go with Community and run your server-side project on Neo4j Community Edition. And being an open source project, we also put out all our content under a Creative Commons license. So we're very liberal what the interaction and collaboration is about. And something that's also great about a community, a rich community, is that we have a lot of local meetup groups. So right now we have, I think in 28 cities around the world, we have local Neo4j meetup groups, and we want to grow that so that we cover most of the areas and everyone can find a local Neo4j meetup group nearby to discuss and exchange ideas and give feedback and learn new things and be creative and interactive. Yeah, so I must say, personally, I really love working in an open source project because that's a really incredible place to be.
Michael, if listeners would like to learn more about Neo4j, how can they do that?
So there's a lot of content about Neo4j out there. So we have a website at neo4j.org, also a blog, and we have lots of videos online from our conference from Graph Connect, which we want to repeat in 2013 in lots of different places. From our meetup groups. So as I said, we have all these local meetup groups, which are really a great resource and great place to learn. From our Google group, so we have a really active Google group where people can ask questions, other people explain graph concepts or help them. And also on Stack Overflow, there are lots of questions about Neo4j, and they are answered there as well. And we also run regular webinars every week or every other week about topics around graph databases and Neo4j, also customer case studies and customer reports. And easiest way is just to Google for Neo4j and then follow all this information that's out there and read about it. And best of all, it works by get your copy of Neo4j, try it out, and get going. That's the best way of getting graphs after all.
Michael, if listeners would like to follow you or your work, where do you publish on the internet?
So I publish my things at gexp.de. But nowadays, most of my blog posts go actually to blog.neo4j.org. As part of the community team, I tend to write a lot of blogs and more blogs in the community than personal blogs these days.
Michael, thank you very much for speaking to Software Engineering Radio.
You're welcome.
Thanks for listening to SE Radio, an educational program brought to you by IEEE Software Magazine. For more information about the podcast, including other episodes, visit our website at se-radio.net. To support us, you can advertise SE Radio by clicking the Dig, Reddit, Delicious, or /dot buttons on the site, or by talking about us on Facebook, Twitter, or your own blog. If you have feedback specific to an episode, please use the commenting feature on the site so that other listeners can respond to your comments as well. This and all other episodes of SE Radio is licensed under the Creative Commons 2.5 license. Please see the website for details. Thanks again for your support.